So before we begin to solve this question using work energy theorem, I have a couple of questions for you here. What do you think is the significance of the word, the phrase, the net work done, number one? And number two, what is the meaning or what is the significance of the phrase by all the forces? So if you're making notes along with this, I would suggest you take a take an example, consider a body which is doing work, and then find out what would this mean, the net work done and all forces acting on it. Okay. So what is work energy theorem? Says it states that the net work done by all forces on a body is equal to the change in its kinetic energy. Okay. Now, when we say change in kinetic energy, what do we mean? We mean that the net work is final kinetic energy minus initial kinetic energy, which is half m v final square minus half mv initial square. Okay. Now, in this problem, we have two motion, downward and the upward motion. What does that mean? The downward motion means the ball is traveling through a height of 10 meter and it's reaching the ground. The upward motion would mean that the ball is moving from the ground towards its maximum height of 5 meter. And we will have to now apply work energy theorem for both the cases. During the downward motion, the free fall means that the only force which is acting on this body is gravity. So gravity is the only force which is which is doing any work here. Okay. There are no other forces involved. What would that mean? No other forces, say drag, say other air friction or any other wind. No, there are no other forces that is involved during this motion, which means the only force which is doing the work is gravity, which means work done by gravity will be equal to change in kinetic energy, which is kinetic energy, the difference between kinetic energy initial and kinetic energy final. Now, the work done by gravity will be kinetic energy final minus kinetic energy initial. So if we apply work energy theorem for the downward motion, how do we do this? We first find out the kinetic energy at the top. At the top, when it is just dropped, the height is equal to 10 meters, right? So this height is equal to 10 meter. And what is the speed here? Since it is dropped from rest, speed is equal to 0, and therefore the kinetic energy at top, which is k initial, will be equal to 0. Now, what's the kinetic energy at the bottom? Which whatever velocity it reaches, say v, half mv square. Potential energy we do not need to directly find in the theorem because we know that the gravity does the work mgh1 as it falls. Now, I would like to take you through this one more time in detail, but not in this session, of course. So kinetic energy at the top is kinetic energy initially equal to 0. At the bottom is kinetic energy half mv1 square. And work done by gravity is mgh1. How is work done by gravity mgh1? I would suggest we will consider that in detail while we go for the written explained notes. Okay. As of now, let us just try to understand a bit about what the theorem is in its broader perspective. Okay. Yes, I do understand that there is an element of confusion here, and trust me, it will be very uh, briefly explained when we go through the written explanation. Okay. So as of now, ball is dropped from rest. Kinetic energy initial is 0. Final is half mv1 square. And work done by gravity as it moves down is mgh1. Okay. So kinetic energy initial is k is 0. Final is half mv1 square. And work done by gravity, mg, as it moves down is mgh1. Now, how do we equate this? What is work energy theorem? work done is equal to change in kinetic energy. So work done by gravity will now be equal to half mv1 squared minus half m u square, which is 0. So half mv1 square minus 0. So if we just put this in the form of an equation, what we get is work done half mv1 square 0. So work done by gravity Wg will be equal to half mv1 square minus 0, or work done by gravity is equal to half mv1 square. Now work done by gravity, which is Wg, is m into g into h, which is equal to half mv1 square. What is mgh? If we recall the basics of gravitation, mgh is actually gravitational potential energy, which is restored here as the kinetic energy. Substituting the values, cancelling off m, what we get is m1 square is equal to 196, which gives us the value of v1 as 14. Okay. Now coming for the rebound motion, it's not 10 meter. Instead, the ball reaches only a height of 5 meter, right? It was dropped from 10, but it reaches only a height of 5 meter. Immediately after rebounding from the ground, the height is equal to 0, right? And the speed, so immediately after being dropped, the height is equal to 0, and it changes its motion. It starts moving upwards, and the speed now is v2. So it approached with v1 and is now going up with v2. As the ball goes up, gravity does negative work. Negative because it is opposing, and therefore minus mgh2. So one more time. At the top, at the top here, the height is 5 meter. And what will be the speed? Since this object is momentarily at rest at the maximum height 5 meter, the velocity here would be equal to 0. Therefore, kinetic energy at the top will also be equal to 0. At the top, not at the bottom. So the bottom is half mv2 square. Now, during the upward motion, what happens is the only force acting is gravity, which in this case does negative work. What does that mean? It means that the object is going up, displacement is acting upwards, and the force is acting downwards. So it is opposing the motion here. And when it is opposing the motion, the work done is negative. As a result of which, gravity acting downwards causes high kinetic energy to be converted to potential energy, because kinetic energy reduces and it is converted totally to potential energy. Applying work energy theorem, work done by gravity, the negative work, minus mg, minus mgh2, will be equal to change in kinetic energy, which is final kinetic energy minus initial kinetic energy. Wg is minus mgh2. Kinetic energy final is 0. 0 minus kinetic energy initial is minus half mv2 square. Okay. Which gives us v2 square is equal to 98, and v2 therefore is root of 98, close to 9.9. So downward motion, distance traveled is 10 meter. Equation is plus mgh1 is equal to half mv1 square, which gives us the value of v1. Likewise, upward motion is mgh2 half mv2 square, which gives us the value of v2. Now this is before impact and after impact. Okay. Now with v1 and v2, we can find out the impulse, which is m into v2 minus v1. v1 is minus 14. Therefore, we get 9.9 minus 14, which gives us 23.9 times mass 0.1. Therefore, the value of impulse is 2.39 kilogram meter per second. Okay. So far, we did this with equations of motion, right? And then we discussed the concept of work energy theorem. And see, yes, I do realize that it's a bit confusing and overwhelming in altogether to connect these two topics at once. And there are many questions in your mind that you feel is not answered during this explanation. We will go through it when we discuss the written part of this. Okay. Now, the point here is just to make sure that you visualize these concepts well to understand how to how to begin the process of visualization. That's what these presentations is taking you through. Okay. Now, all those things which you find is a bit confusing, hopefully, we'll be able to resolve it better while we discuss conservation of mechanical energy theorem. And if there are some things unresolved there as well, then while we go through the written explanation, things would make even more sense in a better way. All right. Okay. Now let's move on to the conservation of mechanical energy theorem and its application in this particular problem.